Okay? And so what we went over last time was how we can get oxidation numbers given a formula here. So for example, let's do COBr4. This complex has a -3 charge. Tell me what my oxidation number on my cobalt is. Everybody take a second. All right, and yeah, you need a periodic table, so just to put one up here. All right, and I will put this exact periodic table on Canvas for you to download, but you should all have a periodic table, right? I mean, it's a chemistry course. You're going to need to look at a periodic table. It's particularly important for this chapter, right? As we discussed with those electron configurations, you're not going to be able to do that unless you know where on the periodic table that element lives. All right, so COBr4 with a -3 charge. Each of these bromines, these bromide ions is really what we would call them, has a charge of -1. I got 4 of them. So I'm going to sum that all up, and that would equal a total amount of negative charge of -4. All right? And what are the sum of my oxidation states in this compound going to equal? That net charge, that -3. Right? So if I got 4 bromides together, that's -4. If everything sums up to -3, what's going to go here? +1. Right? 1 minus 4 is -3. So that means my cobalt has an oxidation number of +1. All right. Cool. So in this case, again, oxidation number +1. We're going to see a lot of polyatomic ions as well. These are these monatomic ions, right? Picking that word apart. What does the mon mean? Monatomic? 1. So these are the chloride or bromide ion, rather, is an example of a monatomic ion. How do we deal with something like this, for example? It's going to be the same game, except for we need to know what the charge on that cyanide ion is. All right, luckily this isn't something we have to have memorized. We just need to be able to use our resources. And for this particular chapter, one of our constants pages is going to have this chart in the middle here. Okay, so what we're going to do is for this polyatomic ion, this cyanide ion, we're going to go to our chart. And we're going to see that each of these cyanide ions have a charge of -1. All right, so then we're going to play the same game. Don't worry, we'll talk about the rest of this chart here in a bit. For right now, we're just looking at this symbol and the charges. Again, I can see my CN has a charge of -1. So I'm going to go back here. I have 6 of them, each with that charge of -1. All right, so those add up together to be -6. What's the net charge on this compound? 0, right? There's nothing written in that top right-hand corner, so that means a net charge of 0. So then that chromium ion has to have an oxidation number of +3. All right, so let's do another one. Let's do, no, I lied. All right, MO2, CO3, 3. All right, so we'll go back to this chart here. I'll put it down over here so we can see it a little bit more clearly. All right, so each of these carbonate ions has a charge of -2. Right, so whoops, MO. So I got 3 of them. Each one has a charge of -2. So sum them all up, that's a charge of -6. Everything's going to sum to 0 because that's the net charge on that compound. So my positive charge, my total amount of positive charge is +6. In this case, I have 2 of these molybdenum ions, MO. So if they add up to +6, what's the oxidation number on each of them? +3. All right, let's do one more here. All right, so anybody got it? Yeah, it might seem like a little bit of a trick question, but we're going to play the exact same game. I got 4 waters. What's the charge on each of those water molecules? 0, right? Water doesn't have a charge. And everything's got to sum up to +2 because that's the net charge on this compound. So that means my iron ion has to have a charge of +2. All right, some of these ligands are charged. Some of these ligands are neutral. Okay? All right. So we talked about oxidation number. All right, now for these transition metal complexes, we want to be able to determine the coordination number. Okay. Our coordination number is the total number of donor sites on our transition metal. So if we did, for example, a compound like FeCl4 with a -1 charge, all right, based on what we learned before, you should be able to give me the oxidation number. Everybody take a second and give me the oxidation number. All right, so my oxidation number would be +3. Each of those chlorides are -1. I got 4 of them, and the total negative charge is -1. So that means my iron must be +3. But now I could also ask you for the coordination number. And for that, we're going to again go to our constants page. And we're going to see that for each one of these ligands, we have another part of this chart here, which is the total number of donor atoms in that ligand. Right? So for each chloride, how many donor atoms are there? Just the one, right? So if I go here, again, the coordination number is the total number of donor sites. I have 4 chlorines, each just has 1 donor atom. So this would be a coordination number of 4, 1 for each of those chlorides. All right, how did I get that? I did 4 times 1. 4 was the number of chlorines, and 1 is the number of donor sites per chlorine. All right, so focusing just on, for the sake of time, we should be able to do oxidation numbers as well, but just for the sake of time, just looking at coordination number. What if I had something like give me the coordination number in these 2 compounds here. All right, again, looking at coordination number. I have 3 of these carbonate ions. Each one has how many donor sites? 2, right? That's what my chart's telling me. So that would give me a coordination number of 6 for that complex. Right? Number of ligands times the number of donor sites on that ligand. What about for this one here? Now I have 2 ligands on there, but it's going to be the same game. I have 2 chlorines. Each one has a number. How many donor sites? Just 1. And then I have this EN thing here. What the heck is that? I just got to be able to use my chart. 2 times the number of donor sites on that ligand, which is 2. All right, so this gives me a total of 6, a coordination number of 6 for this compound as well. All right, again, 2 chlorines times that 1 donor site on my chlorine plus my 2 ENs times the number of donor sites on those ENs. All right, so let's do one more here just to make sure we got it down. All right, what do we got? Who thinks it's 3? Raise your hand. Who thinks it's 4? Raise your hand. All right, cool. All right. We got the name of the game here, right? So I have 2 ammonias. Each one has 1 donor site. I have 1 glycine. Each one has 2 donor sites. So that's a coordination number of 4. All right. Are these formulas here big and ugly and intimidating? Yes, they absolutely are, right? But if we just pick it apart step by step, it's not too bad. Again, it's all about using our resources, using this table here, all right? And now, talking about intimidation, we're going to go one extra step here and now learn how to name our complexes. Okay, that's going to be using these 3 charts here. And again, not about memorizing, just being able to use these charts to come up with the name of these transition metal complexes. All right, so first I'm just going to tell you a name, and you're going to trust me, and we're going to pick it apart and see where each of these components come from, and then we'll work on putting them together ourselves. All right? Okay, so FeCl4 with a +2 charge. This is tetrachloro iron 6. All right, so let's pick this name apart. Where do we think the tetra comes from? This is how many chlorines I have, right? So if we look at this chart here, we see that tetra corresponds to 4 ligands, right? Since I have 4 chlorines, so this is just the number of chlorines. What do we think the chloro refers to? Which ligand I have, right? So this is my ligand identity. Where do we think the iron comes from? The fact that it's iron, right? So that's my transition metal. All right, and then probably the least obvious part here, how the heck did I get 6? This is the oxidation number, okay? So not the coordination number. We will need the coordination number. It's very important for the geometry, which is something that we'll learn next week. Right here, this 6, this is that oxidation number. So in order to name my compound, I would first have to figure out what the oxidation number of my iron is. I have 4 chlorides, right? So if I'm going to do it the long way here, Cl minus 1, Cl minus 1, Cl minus 1, Cl minus 1. It's a total amount of negative charge of -4. I have that net charge of +2, so this has to sum to +2. That's how I get a +6 on that iron. Okay, so the last part, the Roman numerals, corresponds to the oxidation number, which is actually the same as when you were naming ionic compounds back in general chemistry, right? The charge goes in Roman numerals. But that's why we first had to learn that skill of figuring out our oxidation number. All right, so I'm going to do a fairly simple one, and I want you guys to see if you can't put the name together using our resources here. Okay, so let's do CO. All right, so just by analogy with what we did with our tetrachloro iron 6, see if you can't put together the name of this complex here. All right, so I have 3 of my ligands. So I'm going to refer to 3 ligands with that prefix tri. My ligand ID, this NH3, we call those amines, right? So this is triamine. My metal, CO, is cobalt. All right, and then the oxidation number on this cobalt would be 3, right? It's a neutral ligand, so it's just going to be the same as that net charge. So triamine cobalt 3. All right, so let's just kind of explicitly state our rules here. We are now naming transition metal complexes. All right, so this is what we're going to do this as our example compound here. Everybody take a second and put down that formula so we can go back to our other page. All right, and see if you can't name this compound here. Name this transition metal compound. All right, so again, I have 2 of these bromines, so I'm going to use that prefix di. What's the name of my bromine ligand? Bromo, right? So this thing here we refer to as a bromo group. By far the coolest named of all the groups. Okay, here's my bromo group. I'm going to name my transition metal. Cr is chromium. All right, and I'm trying to run out of room here. All right, and then probably the hardest part of this is that oxidation number. What's the oxidation number going to be? Yeah, be careful. It's not just 1. I got to go through that same process that we've been going through. Bromine is a negatively charged ligand. I got 2 of them. They got to sum up to +1, which means that my chromium has an oxidation number of 3. So dibromo chromium 3. Just rolls off the tongue, huh? All right, so again, the components of this name is our prefix, which refers to the number of ligands. The name of the ligand itself. the name of the transition metal. And then lastly, that third component, or that fourth component, is the oxidation number. All right, so now, of course, I'm going to go in here and complicate things a little bit. All right, so now let's look at a compound like, let's do titanium. All right. So most of this procedure is going to be the same. All right. With the exception of the prefixes that we use. So let's just put this down over here. Okay. If we have one donor atom, these are what we call monodentate ligands. Damn it. But if we have more than one donor atom, these are what we call polydentate ligands. Right? So dentate is number of donors. Monodentate ligands have one donor. Polydentate ligands have more than one donor. The reason why this is important is because we have different prefixes for monodentate ligands. Those are our normal ones, the di, tri, tetra business. But we have a different set for polydentate ligands. All right, look, I didn't make the rules, all right? I don't know why the chemistry gods decided to name these things differently, but they did, okay? So if there's more than one donor atom, we got to use this other set of prefixes, are polydentate ligands. So in this case, I have two. So I'm going to use the prefix not di, but bis. I'm again going to name my ligand. I'm going to look it up for En. Again, just rolls off the tongue, ethylene diamine. And I don't know why, but for polydentate ligands, they put the ligand name in parentheses. All right, so I'm going to run out of room here, so let me just do it over here. So this is bis, ethylene, diamine, titanium, and then that En was a neutral ligand, so my oxidation number is just 4. All right, so when we have polydentate ligands, we're going to, again, the first thing is going to be the number of ligands. But we got to use our polydentate prefix. I'm again going to put the name or the ID of that ligand. But I'm going to put it in parentheses. I got my transition metal. And finally, the oxidation number on that transition metal. All right, so we gotta switch up just a little bit our procedure for when we have a polydentate ligand. All right, and then one more curveball here is going to be how we deal with negatively charged complexes. So let's do an example. I'm not terribly creative. I feel like I'm recycling through the same transition metals here, but let's go nickel. Oops. All right, so now we have this negatively charged complex. Let me make room. Right, I got this net negative charge on this compound. Everything kind of starts out the same. All right, so going back to our list here. Let me get rid of all this crap. What did I do? CL? Yeah, my bad. I'm going to still use, this is a what? Poly or monodentate ligand? Mono. So I'm still going to use my mono ligand section. 4 would be tetra. So tetra, chloro. All right, chloro because it's a chlorine. But the difference is how I'm going to refer to the transition metal. The overall complex charge is negative. So now I got to use this chart here. Instead of referring to it as nickel, I'm going to use the anion name because it's negatively charged, and it's going to become nickelate. Tetrachloronickelate. And then I'm still going to put that oxidation number, which in this case is 3. All right, so again, if we're going to pick this apart, tetrachloronickelate 3. Same basic components. I have my number of ligands. Whoops. I have the name of those ligands. But now I'm referring to my transition metal with the anion name, and then still including that oxidation number. All right, so again, number of ligands, my ligand name, and then I'm going to use the anion name of my transition metal, and then finally that oxidation number. All right, so for the remaining time here, let's just try to do some examples. I'm going to put down some formulas. You're going to try to name them on your own, and then I'll come in with the answers. Let me see if I can't move this thing up. There we go. Give us a little bit more room. Ah. Not gold. Silver. AU is gold. All right, so these four complexes here, everybody take a second and see if you can't use our resources here to put together the name of these three complexes. All right, and in the interest of time, I'm going to give you guys a head start, and then I'm just going to kind of quietly fill them in. So if you're stuck, you can look up. But again, try to do as much as you can on your own here. AG is silver, yes. All right, so just real quick in this last minute. The first one, I got 4 amines, 4 NH3s. So that's tetraamine, silver, and then the oxidation number would be 1. So tetraamine silver 1. My glycinato group is a polydentate group. So instead of referring to it as a di, I'm going to use the polydentate prefix bis. So bis, and then in parentheses, glycinato, iron 4. And then the last one is a negatively charged complex. So it's going to be hexabromo, but I'm going to use the anion name cobaltate 2.